Welcome back, everyone. The next section will be presented by Chris Lam from UK. His topic is reproducible builds, revealing the original promise of free software. Chris is a polyglot freelance computer programmer who is the author of dozens of free projects and contributor to hundreds of others. And he has been an official Debian developer since 2008 and is currently highly active in reproducible builds projects, where he has been awarded a grant from the Core Infrastructure Initiative to fund his work in this area. In his spare time, he's an avid classical musician. Let's welcome Chris.
Good morning, everyone. Can everyone hear me okay? That's good. Brilliant. Thank you for attending my talk. My name is Chris Lam. Thank you very much for the introduction. And since then, I've actually been elected the Debian project leader for 2017. So that's very exciting, and very proud to represent Debian here today and in general. So I'm here to talk to you about reproducible builds. So we've already got a little bit about me, so we'll skip over that. So before we talk about reproducible builds itself, we'll have to talk about what problem it tries to solve. So what is the problem? So free software and open source software is really great in many ways, but in one particular way, we can always analyze the source code for malicious flaws. So for example, if we're running Nginx or any other web server in production, what we can do is download the source code and look through each line by line and see whether there are any malicious flaws being added by third parties. For example, someone might have submitted a patch that just adds this very simple feature, but in actual fact, it ends up introducing a backdoor, sort of a secret key, so a skeleton key into the software itself, which you wouldn't want. No one wants that at all. And so, free software is uniquely positioned in this way because you can download the source code and see whether people have tried to sneak in those kind of things into the code. The sort of problem arises is that people don't actually tend to they don't tend to download the source code and then compile that version and then run it on their own machines. They tend to use the distributions provided pre-compiled packages, or as on some platforms, for example on Windows, even if it's free software, you might be just downloading an exe. So whilst the underlying software might be free software, people are still downloading an installer package because the user convenience is much more convenient to do that than to download the source code, install Visual Studio, get everything, all the dependencies, and then run that. Which means there's a disconnect between the two. So whilst you could have spent hours and hours checking the source code for flaws, you've then just downloaded an entirely separate executable and run that. And so, can you really trust the compilation process? Can you trust who is doing that compilation process? Can you trust the processes behind that compilation? So, if you were going to target a bunch of people and you wanted to gain access to their systems, who would you go after and to try and use this attack? Well, the first one is to go after build networks. So I've already talked about the distributions packages. So this is when you do apt-get install blah. That's going to install the blah package that's been pre-compiled for you on what's called a build network, which is basically a bunch of servers that are somewhere in the cloud or in some university hosting environment. So if you could compromise one of these build networks, then you could insert malicious code into millions of people's software. And whilst the original source code would look absolutely fine, when it went through one of these build networks, that's where the malicious flaws would get secretly added, and then the outputs of those would be installed on lots of different people's computers. Not ideal. So does this actually happen? Well, yes. Here's the Apache project's infrastructure. There's a backdoor added to this FTP server, which is being hosted. Again, the source code that was available on the site was not affected. It was just the downloads. Here's one in the iOS App Store. Not sure if I have the image, but there's another one. FreeBSD, Kingslayer, PHP, MyAdmin downloaded, Red Hat, Windows Update, kernel.org was compromised, Juniper firewalls, etc., VSFTP, even the Free Software Foundation software repository was compromised in this sense. So yes, this is not a hypothetical attack vector. So developers' machines are other ones. So say you were running, say you were a developer and you were writing a Bitcoin wallet software, fair enough, and you released the source code, etc. I could specifically target your machine for some malware, and then if you downloaded and installed that, you would continue to produce your Bitcoin wallet software, and you'd release the source code of this, and the source code would look absolutely fine. It would be perfect. There are no security holes. But the executables you produce by your compiler could be modified by this malware that you're running on this machine, which is very, very dangerous, because you would then swear blind that you aren't adding any backdoors, yet the software that you're producing contains backdoors, which is very, very tricky and very pernicious. So even the most honest person can be vulnerable in this way. So here's one example of how you could attack, not necessarily by targeting malware at you, but called the evil maid. So-called where you have you leave your laptop in a hotel, and an evil maid, evil housekeeping comes in and puts in a secret USB stick. It's happened. So it's not only the developers' machines that are vulnerable, the developers themselves. So let's go back to our example of the honest Bitcoin wallet software person. Well, he may be a very reputable gentleman or lady, but for example, they're still humans, and they're still vulnerable to, for example, blackmail attacks. Or even if they aren't vulnerable to blackmail, they may be vulnerable to just a baseball bat. I mean, most humans are. So, for example, say you had access to hundreds of millions of people's Bitcoin wallets, I'm guessing that would make you a rather rich person. And so if you do a trade-off between how much it would cost to send a bunch of, rather tough-looking guys with baseball bats and petrol around to your house, it gets a little scary. The mathematics there aren't very favourable. So this is where I would say, continue to release your source code, etc., etc. But when you go and make your, for example, make your Windows binary an exe, just insert this small bit of code, insert this extra password. Otherwise, wouldn't want anything to happen to your sister. You know what I mean? Just saying. It's very, very scary, and we not only do not want that to happen, we don't want people to even try and attempt it. So this is what Reproducible Builds tries to prevent against: attacks against build networks, against the developers' machines, and against the developers themselves, because they're highly vulnerable in a personal sense. So again, this is not a hypothetical attack. The University of Calgary was subject to a blackmail. Here's another, you can find all these links on the slides later. He was put in somewhat blackmailed to put in a backdoor into a botnet here. And here's the recent NHS cyber attack, where this is another blackmail-based thing. So we'll remove this software from your computer if you pay us in some Bitcoin. So the other purpose of Reproducible Builds not only is to ensure that the binaries that you're running don't contain any backdoors and correspond to the original source code. Sometimes you definitely want to ensure that the binaries that you're running correspond to the source code for other reasons. So if government have released some source code, say for voting machines and things like that, and say, this is the code for the voting machine, and then you go to a voting machine, how do you actually know, how can you trust them? Maybe there's been some version mismatch, maybe they're running something completely different. You're not really sure. Medical software. A lot of this code, you say you could get access to it if you're running software on your pacemaker or on some sort of heart rate monitor or anything like that, and the medical company provides you with the source code of that. You want to actually have some sort of idea that what they've given you is actually the software that's running on the device. It could be completely different software. GPL compliance, so this is the general public license from the Free Software Foundation. That says that if you distribute binaries, you must distribute the corresponding source code. Again, you could have binaries on your router firewall and things like that, your sort of Wi-Fi box, and they could be providing you with some source code downloadable from the website. But how do you know they correspond? You just sort of have to trust them in that sense. Software in your car, well, soon you will be self-driving cars, and I'm sure we'll be able to get the source code for some of them. But do you know that the actual code that's running your car on the road at 70 miles an hour is actually the code that's they've provided? You don't know, things like that. So anyway, the general motivation behind reproducible builds is, as I write here, you're meant to read slides out, is to ensure verification that no flaws have been introduced during the compilation process from source to binary. And how do we do this? So what we do first is we ensure that every time we compile a software, we get identical results. And by that I mean, if you run GCC, the C compiler on a piece of code, and you get on some source code, and you get a bit of corresponding binary, you end up with the same exact file every single time you run it. So I mean bit for bit identical, the SHA-1 is the same, the MD5 sum is the same. Then what you do is you ask multiple different people to compare, for example, the hash of the file. So to compare the result that you get. So I would compile a software and get a particular binary. Then I'd ask you to do the same, and you would do it. And then we'd all come around and be like, well, I got this, and I got this, I got this. It's all the same. Okay, brilliant. This means that any attacker or any flaw that gets introduced during the compilation phase must happen simultaneously to everyone. So either an attacker has managed to infect everyone simultaneously, or the attacker has done nothing. So, because otherwise, that someone's would stand out. So if my machine had been compromised, I would get a different result because my binary would contain, for example, a bit of the secret backdoor, the malware, the flaw in the design, whilst your uninfected computer would not contain that flaw. So just an example. So Alice, we're using very short hash here. Alice would compile software and get A, B, C, D, E, F. Bob would also get A, B, C, D, E, F. Okay, pretty good. Carol would get D, E, F, A, B, C. Okay, that's interesting. She gets something else. So we're now suspicious about Carol's build. So what's different about her computer? What's different about her compiler? Remember, we've all started from the same source code, so we should be getting the same results every time. So yeah, that's something to be interested in here. The alternative interpretation is that Alice and Bob's computers have been compromised. Okay, it's something to look into. But in general, the fact that it's now different, we can say there's something going on here. But what causes these non-reproducibility? So obviously, if you've been infected, that's one thing. But software for many years has not been reproducible. So even completely uninfected computers have been producing software that when you compile it each time, you get different results, which is a big problem if you want to provide reproducible builds to the software ecosystem. So one reason is that developers like to include timestamps in their software. So this is the current time of day and things like that. The software might alter its, might end up being different in the end because of different time zones and locales. So this might affect the actual timestamp. So when it prints out the current time in, say, the about message, that might be based on the current time and depending on what time zone you're in. So it doesn't necessarily assume you're in UTC or Greenwich Mean Time. If you compile it on Hong Kong time, it may put you over a date boundary, which therefore means that the binary contains a different date, for example. Sometimes compilation will iterate over a bunch of files in a directory, and on Unix file systems, that's not specified to be in a particular order. So it's not necessarily going to be in alphabetical order. So sometimes the binary will end up having slightly different ordered contents inside. The actual functioning of the binary may be the same, but because it's sort of looked at various input files in a different order than before, it will end up with a different result at the end. Very similar to this, if it loops over some sort of dictionary or key hashing, these typically are again not, they don't necessarily return their results in alphabetical order. So this is like a Python dict or a Perl hash, and things like that. If you do, for example, in Python for x in dict, my dict, then it will give you the results in a random order. And so when they get put onto, if the output of the binary depends on that order, then it's going to have a different result every time. Again, the functioning of this binary may be identical in every case, but the fact that the binary itself is different causes issues for reproducibility. Also, things on the environment surrounding the compilation environment can get sucked in. So, for example, the current user ID or the name of the user in environment variables might get saved to various files for debugging reasons and things like that. So, yeah. So these are all things that mean that if Carol and Bob and Alice came together, because they have different timestamps, for example, they're compiling at different times, they're in different locales, etc., they'll get different results. And we want to remove all of those when doing reproducible builds, so we get a bigger chance that people's binaries are the same, and that's the way we can then compare and then see whether our machines have been compromised in this sense. Oh, another one, build paths. So I might be building in my home directory whilst you be building in your home directory. So this is very common and often gets put into the end result of the binary. So apart from securing developers' machines, build networks, etc., and providing a lot of trust and security, there are many technical advantages when you adopt reproducible builds. So, for example, you can detect accidentally corrupted build environments. So, say you're a developer, you like to try out things. So you've installed an experimental version of some library, but you've just forgotten about it because you did it at 4 a.m. last night with a little bit too much coffee and Red Bull. You then wake up the next day or whatever, and you start doing some other things like that, and you've forgotten you've installed all these experimental crazy libraries, and then so when you go and compare your result with someone else, it's different, and it's because you've installed it, say for example, a very highly new version that you probably shouldn't be running anyway. So I guess that's one way of saying a corrupted build environment and things like that, or just finding mistakes in the way you've set up your compiler and things like that. It's much easier to test revisions and changes. So for example, if you want to remove a bunch of code, what you could do is you can compile it with the code, get rid of a bunch of code, compile it again. Now if you have a reproducible build, and you have the exact same binary before and after you remove this code, well, this code wasn't doing anything because the binary hasn't changed. So it's absolutely certain you can just remove it. Just because it just can't be used, it can't be functioning because it doesn't exist in the output. The other reason is that if you do make any small change, the only changes that you'll see in the resulting binaries should be corresponding to the changes you've just made. So if you've only made one little, this should be if not instead of if, then that should be reflected in a very, very small change within the resulting binary and not hidden within all these timestamps and dates and things like that. It's very easy to see just the changes that are required. There's also generally there's no unreliable behaviour. One thing I didn't mention before with the thing causes of non-reproducibility is using timing or accessing the internet and things like that. When you have a reproducible build, by definition, you can't do those sort of things. You can't add profile information because it means that people get different results each time. So therefore, you immediately remove a whole bunch of non-determinism from your build, which is very good. This also means it's faster to build because each time you're changing very little. So you're not only saving time in terms of compilation, because you get greater cache hits. So this is where, well, this file has already been compiled before. It hasn't changed. It can't change because there's no causes of unreproducible behavior. So therefore, we don't need to recompile it again. And so that saves you time and therefore money if you're using a cloud service. Money if you're a salaried employee, it's less time. Time is money. And you're also saving CO2 because you're just not burning CPU cycles. This is one thing that pushed Google over the edge, introducing more reproducible builds. Is that they were spending so much time compiling and things like that. When they got greater cache hits, everything was just a lot faster. And if you can save the environment at the same time, amazing. So I'm going to very briefly talk about reproducible builds inside Debian. What we do is we continuously test building every single package twice, and each time we call them the A and the B build. And in the A build, between them we try and vary as many things as possible to deliberately try and surface and raise causes of reproducibility. So we change the time and date between them, we change the host name, we change the time zone, we change the kernel, we change the physical machine, we change just as much as possible. Informally we call it the sort of the torture test. So if a piece of software is non-reproducible, this should hopefully show it up. And we've got some pretty good results. So green is the number of reproducible packages in Debian, and orange is the unreproducible packages. So as you can see, we're generally trending up towards the total. The reason the graph expands itself, so if you if you see that the beginning over here on the left is lower than on the right, it's because Debian, whilst we've been working on this project, the number of packages in Debian has been increasing. So a bit of a moving target. If you're curious, the reason for this dip is that we introduced a variation on the build path. So this is where between the A and the B build, we would select different path to building. So for example, instead of always building in the same directory, we might build in temp A on the A build and temp B on the B build. And this causes a lot of unreproducible packages, hence the drop. But it's not just Debian. There's a whole bunch of other people that are extremely interested in this. These are other operating systems you may have heard of that are, and this list is ready and complete. A lot of people outside of Debian very involved, and a lot of these projects are now using what was originally the Debian test framework to test their software. And we've had 2 summits meetings of about 60 people, one in Athens and one in Berlin, and we plan to have another one at the end of this year. We also have a bunch of generic tools, which I'll show you in a second, that can be used to diagnose and surface non-reproducible packages. So quality assurance. So this is one of the tools in itself. Diffoscope, what we call it, our diff on steroids. So anyone who's familiar with GitHub will know the sort of diff layout, the red and the green. This code was removed, this was added. This is what we call a diff on steroids. So you can give it 2 files of almost arbitrary type, and it will unpack them and give you a human-readable diff between them. So, for example, you could give it 2 ISO files, CD-ROM images files, and within that CD-ROM there could be a a zip file, and within that zip file there could be a PDF, and in that PDF could be a PNG image. And it'll try and give you a human-readable difference between that, even though it's embedded in all of these formats that are individually compressed and things like that. If you did that with a normal diff tool, it'll just give you a completely obscure binary change between the two. So you can hear, there's a different example, but at the top that's when you give it to SQL-like databases, it will actually show you the difference in commands that we use to populate the SQL database. And at the bottom, there's an XML file, which wasn't normally formatted like that, but Diffoscope formatted it in a nicely indented way, and then highlighted the difference between that. So you can very quickly see that, for some reason on the A build, it has 6 at the end of there, and on the B build, it has 7 on the end. So this is an extremely useful tool for doing any sort of diff work involving files. So I'm going to skip over some of these interesting bugs that we found, because, as I said, there's not only technical advantages of reproducible builds, there's not only security advantages, but also these QA benefits. You can find these rather interesting, curious bugs that have surfaced whilst running through. For example, this package failed to build 0.46% of the time. So most of the time it would work, but 0.5% of the time it wouldn't fail to build. Very interesting, very interesting. Here's another one that had a different result if you built it within the hour of the code being released. Why not? Why not? Things like that. So the future work. So the source code still remains vulnerable. So in reproducible builds, we always assume that the source code is absolutely free of bugs, absolutely free of malware, absolutely free of things like that. That just isn't true. But we start with that as an assumption. So we just say, okay, given a piece of source code, we're just trying to plug up the link between the source code and the binaries. So the source code will always remain vulnerable to bugs, will always remain vulnerable to security flaws, always remain vulnerable to people submitting extra changes to it which contain nefarious backdoors and things like that. The other problem is making reproducibility meaningful to end users. So for example, when a packet, if you went to install a package from, say, an Ubuntu or Debian archive, and it said this package is not reproducible, what does that really mean to an end user? Will they understand that? What does that mean as well, in the sense of, if you remember the Alice, Carol and Bob, 2 out of 3 people had one idea of what the resulting binary should be. Does that mean the package is unreproducible? Which one is the trusted one? This is a difficult thing to present to end users in a very useful and tangible and helpful way. So if you're interested in a bit more, you can visit our website at reproducible-builds.org. We have an IRC room, Reproducible Builds, on oftc.net. We have now monthly IRC meetings. We're a very friendly bunch. It's not Debian specific at all. Any distributions are welcome. And you can also check your own software. So if you do generate any binaries, why don't you create one today, and then tomorrow create it again, and see if you get the exact same results. You might find the results surprising. I was certainly surprised the first time I tried this piece of software. Oh, no, there'd be nothing in there. This is all a silly idea, hypothetical. But no. My actual binaries are different each time. And I'd just like to thank the Linux Foundation, and specifically the Core Infrastructure Initiative, for help funding some work in this area, with a number of other team members on the Reproducible Builds team. Thank you very much to them. So if you've got any questions, feel free to ask them now, or you can contact me later, things like that. But yeah, I'd like to thank you for your attention today, and yes, thank you. So if there are any questions in the room, everyone here. Do we need a microphone? Is that?
How sensitive is this to compiler versions?
The question is, how sensitive is it to compiler versions? It's, in general, not. The compiler itself generally doesn't make, so between GCC X and X+1 has usually very little difference. It's usually the libraries, like glibc and things like that, and as those change far more often than GCC version, because GCC doesn't actually release that often, things like that, those tend to be a bigger cause of non-reproducibility. So the actual GCC version, I mean, sure, if you jump between that version 5 and version 6 or something, yeah. And it'll depend a lot more on optimization flags than anything else. So some of the advanced ones, and therefore it may affect different architectures, faster moving architectures between GCC versions quicker than, say, the vanilla x86 and things like that. The biggest change would be, I suppose, that newer GCC versions have some of our own patches to reduce some, in particular, build path variation. And so if you're using an old version which does not support this tool to remove non-reproducibility, it is therefore implicit. Yeah, but that should only happen once whilst you move to a version that does support the flags and things like that.
Yeah, maybe time is running out, so one last question. Any questions? Yeah.
Have you tried
The question is, have we tried to have reproducible kernels? The answer is yes. The Linux kernel itself is reproducible, which is great. That was thanks to some work by Ben Hutchings. Unfortunately, the Debian Linux kernel packages are still not reproducible. This is due to something in the documentation generator, things like that. So it's the kernel itself is reproducible, yes, which is really good. And so that means that, and this has also been shown in projects like Coreboot, the slightly cut down firmware router distributions. They can be reproducible and things like that, and then based on the Linux kernel. So yeah, so the kernel, yeah, it's good. Brilliant. Thank you very much. I'd just like to add, I've got some Debian stickers here. You can come and grab them. Yeah, brilliant. Great for your laptop. Thank you very much.